We are talking about rate in electrical systems in this lesson, so we have our learning goals listed here. If you want to browse through those, that's fine, but in general we're going to be talking about how voltage can move a charge through a system. So our bell ringer for the lesson here is name an electrical system and explain why it's important for a technician to understand electrical rate in that system. So here is kind of the important thing to think about, and you don't exactly know what the electrical rate is. Okay, so just think about what rate may be in an electrical system. So remember, rate is a number of things or measured quantity over a time, right? So that's just rate in any system. In your explanation, do not give answers such as, so the system doesn't fry, break, or technician can fix it, etc. Explain your answer using rates of electricity. So let's think about what rates in electricity were. We've talked about them before. So we have things in electrical systems. We have volts, and we have amps, and we have ohms. Those are the three basic things that are involved in an electrical system. Remember, voltage, I'm kind of jumping ahead here, but voltage is what moves the electricity through the system. And ohms is a resistance value, so amps is my value or my rate. Okay? So an electrical system that would be using amps would be pretty much anything. Alright, so you could talk about a battery in a vehicle. You could talk about the electricity going through the wires in a vehicle. You could talk about a factory, right? Because we could talk about the electricity going to the machines in the factory. Alright, so what happens if we have electricity moving too fast? Well, usually when we have electricity moving too fast, that's going to heat wires up, which could melt wires. Okay, because things that are moving faster will create more friction and more heat. It also may make the machine go faster itself. So if we think about the little DC motor that we've worked with before, okay, so our little motor that we had the little shaft on, and we lifted some weights or something with that, if we punch more charge into that, that's going to speed up, and that could make the motor move faster, which we don't want that to happen. We want to have that controlled, right? So it's important to control the amount of current going into the system so we can control the machines. So any system, you could think of several systems here that use electricity. It's important just to talk about the amount of charge going into that system and what it does if we have charge moving too fast or too slow. I guess I didn't talk about the too slow, but in general that's going to make the machine be less efficient, and it'll make the machine, it could make the machine move slower or not operate at all. So, as I said, I kind of jumped ahead of myself in my explanation, but what is the prime mover in an electrical system? So what is going to move the charge in the system here? So voltage difference is the prime mover, because, and we have to say difference here because remember, if you have 12 volts here, say we have a battery that's 12 volts here and a battery that's 12 volts here, and we try to move charge from one to the next, right? So we have our terminals there, anodes and cathodes. If we try to move charge from one to the other, it's not going to do anything because this is 12 volts and that's 12 volts. However, if we said that this were a 6-volt battery, then there will be charge moving between the two of them. There is going to be a voltage measure in this wire because there would be a potential difference or a voltage difference. Okay, so what is electrical rate? And we already kind of talked about that, but we're going to get more specific here. So I'm going to jump all the way down to the end here. So what is electrical rate? It's the amount of charge, okay, that's given by Q, that flows through a conductor in a unit of time. Okay, and then we already talked about this as well in my explanation for my electrical systems. But what term is given to electrical rate? And that would be current. And current is measured in amps, or its amperage. So the symbol to represent electrical current, hopefully we remember this from previous lessons. You might think about Ohm's law, and that will tell you that the symbol in our equation is going to be an I. And the unit used to measure current is the ampere and amps. And we talk about a system, we talk about the amperage of a system, and it's written as capital A, like so. So if we had 5 amps, it would be 5 with a capital A. So current is the rate of movement of charges, and we have our equation, our formula down here below. Okay, so current is charge moved over elapsed time, and amperes, so we could solve this, or we could just use the units here. Amperes is going to be equal to coulombs over seconds. So we want to find how many coulombs of charge are moved in how many seconds. So if we think about a unit here, or units, so an amp is just a coulomb per second. Okay, so 1 amp is defined as 1 coulomb in 1 second. So for the purpose of using amps, we do have to use seconds. Alright, so this is our equation. Make sure you have that down somewhere, because we are going to use that right here. So a DC motor operates at a rate of 10 amperes for 10 seconds. How much charge, or coulombs, moves through the motor? So let's write our equation down just so we get some practice with it. Amps, or current, is going to be charge over time, and we know that this is measured in coulombs, time is measured in seconds, amps are measured, or current, excuse me, is measured in amps. So we're going to write down everything we have. So 10 amperes, that's I, remember, that's 10 amps. Okay, and then we have time of 10 seconds. And then we're going to plug them into our equation. Okay, so 10 amps goes on the left. I'm looking for the amount of coulombs moved. Okay, oops, and my time is 10 seconds. So solve this little algebra problem here now. If we have the 10 seconds in the bottom and we're solving for Q, we got to get the Q by itself. So we're going to multiply both sides by the 10 seconds. Alright, and that will get rid of that. So my Q, or my coulombs, will be 10 times 10, which is 100. So I moved 100 coulombs of charge in those 10 seconds. Okay, so the little DC motor moved 100 coulombs of charge. Alright, let's take care of another one here. So a second DC motor operates for 5 minutes and uses a charge of 225 coulombs. So how many amps are in the system? So now I'm just going to write down the variables that I know and that I don't know. So amps, or current, that's what I'm looking for. Time, that is 5 minutes. And charge is 225 coulombs. Okay, so right away we should recognize that we cannot use minutes. We got to convert. So we want to convert those minutes to seconds. So there are 60 seconds for every minute. So that means our time value is going to be 60 times 5, which is 300 seconds. That's what we're going to use for time. So write out our equation, plug stuff in. So current equals charge over time. So we're going to divide those two values to end up getting 0.75 amps for this DC motor, which is a little bit different than the one up above. Okay, but these two problems, you can kind of see how this equation is fairly basic. It's not too bad. We just have to understand what the variables mean, and if we have to convert, like here, then we should do that. Okay, so we're going to talk about a few things that should kind of seem as review. So we're going to talk about a few things that should seem like review. Okay, so remember we have our types of electric current that we've talked about. Well, there's two of them. We got AC current and DC current. And I have down below here what they are again if you forgot. So AC current or DC current first. So that's direct current, flows only one way, one direction, from negative to positive. Okay, and most often DC is going to be used with batteries, right? Because DC current batteries, they're going to throw out all their charge and then they're done. So they can't, you can recharge them, but you'd have to use some kind of an AC current to recharge that the battery. Okay, so AC current, that's alternating current. So current flows both ways, alternating with electrons constantly changing direction. Okay, so with AC current, there are some things involved with that. I'm kind of jumping the gun here, but we can talk about it now in this lesson and then review it in the next lesson. So AC current, alternating current. So if we talk about things that alternate, you might think of a spring or wavelength. Okay, so alternating current, if we measure that with a thing called an oscilloscope, then we're going to get a wavelength kind of like that. Okay, because with AC current there is a frequency involved, and frequency is measured in hertz. Okay, and the equation for frequency, we're going to review this again next lesson. Frequency is going to be 1 over the period, and this is time it takes to repeat. Okay, so that's the time it takes to repeat itself. And it's really easy to recognize that when we look at something such as a wavelength. Okay, so if you remember from physical science, there are crests and troughs of wavelengths, and there is a period of a wavelength, which you may not have talked about in physical science, but that would be the time it takes for it to repeat itself once. So if it starts here, let's look at this wavelength to see when it starts to repeat. So it goes up and then back down. Yes, it hit 0 again, but it's going down beyond that. Okay, and we're going back up here, and now we're back to start. Okay, so if you look here, kind of trace my pencil here, this would be one complete wavelength. And then we can kind of follow along here, and boom. So in the picture that I have drawn here, I have one wavelength, two wavelengths. So this repeated itself twice. Okay, but if we were given the time value for one wavelength, let's say that took 2 seconds for one wavelength, then I can figure out my frequency. Okay, so if I use this equation here, frequency is going to be 1 over the period, which is the time to repeat, 2 seconds. So that's just 1/2, which would be 0.5 hertz. Okay, so this is just kind of a preview for the next lesson, but alternating current switch directions, it switches around. So this would be, I'm going forward, and then I switch directions going backwards, and I switch direction going forward, switch direction going backwards. When we talk about frequency with AC current, we're talking about how many times it switches per second. Okay, what's the frequency of that electricity? So we want to talk about why AC current is used in homes and businesses. We have discussed this before, so if you remember, this will seem like review. But number one reason, AC current is a lot more economical than DC current. Because remember, DC current, that's a battery most of the time. So in order for us to power homes, we would have to have a ton of batteries. And if your home used a battery or something throughout the day, then you'd have to get another battery the next day and another battery the next day. With AC current, we can just run conductors to the house or high voltage wires and stuff like that, and we can just pump voltage and current, and we can pump charge essentially to the house, and you use your charge whenever you have anything on, and then you turn it off and it stops, and then you turn the thing back on and it's going to use all your charge. But there is no, it's not just completely running out of the system. We have AC, we can switch back and forth, so you can turn it off, you can turn it on, and we can stop flow of electricity to the house, and we don't have to recharge anything. We're just continually running electricity. Okay? Another thing is this thing called voltage decay. Okay, so it says over long distances. So if you're using DC current, then when you have a long wire or something like that, it's going to lose a lot of its voltage. Okay, and AC current's going to lose voltage as well, but DC current has a lot more voltage decay than AC current. And if you think about, like I just talked about, AC current, we have the high voltage wires. We're running electricity over several miles to get from the power plant to the transformers to the house. Okay, and then a little bit of what we just talked about. So commercial power companies generate electrical current that changes directions at a rate of 120 times per second. This is called 60 cycle or 60 hertz alternating current. And now to relate this number with this number, remember my little graph that we just drew a little bit ago. So we have our wavelength here. So this one is going up, so maybe we could start there and say that this is going to change directions. Actually, we have here change directions there after it goes past 0, and then there. So this would be changing directions twice in one wavelength. Okay, this says changes direction at 120 times per second. So if we cut that in half, that would tell me that I have 60 wavelengths in a second, which would give me 60 hertz, right? That's the frequency. So since we're talking about voltage in amps, we have to talk about how to measure it. Okay, so it's important to measure those in an electrical circuit. And we're going to talk about how you set up a voltmeter or an ammeter in the circuit. Okay, so if we want to measure the voltage in a circuit, we can just take that. So this would be a test lead, and that would be another test lead. We can just put it at 2 points in that circuit, and that's going to measure the voltage. Or we can put it at 2 points across a load here. So this might be a resistor or a light bulb. So we can measure the voltage that's going through the resistor. We could put the voltmeter here if we wanted to. So we'd have it out here, and we could measure the voltage going across the switch, and we could see that there would be voltage when the switch is closed and 0 volts when the switch is open. Right, so this would be in parallel. Okay, so a voltmeter, if we want to measure voltage, then we want to go in parallel with the system. So you can kind of see that if I draw a line there, and those are in parallel. All right, now if we talk about an ammeter, that needs to be set up a little bit different. This needs to be set up in line with whatever we're trying to measure. So amperage we're trying to measure in line with everything. If I tried to put an ammeter in parallel like this, I might blow a fuse or something like that in the machine or in the ammeter, and then I'd have to spend time and money to replace the fuse and hopefully not do that again. So I want to put the ammeter in series with everything. So this is put in series. And if you remember doing series and parallel circuits, series would just be in line. So it's like I have this, say I got a battery there, and then I got another battery here. Oops. So these two batteries would add together because they're in series. Now if I put them in parallel, then the batteries would cancel out. Right? So if I had a 2 volt and 2 volt battery hooked together in parallel, so if I had a 2 volt and 2 volt battery hooked together in parallel, remember that looks like it's positive to positive and negative to negative with batteries, then that's not going to give me any reading, or that's not going to give me any voltage. Okay, I wouldn't measure the amps in the system either. So you want ammeters hooked up in series and voltmeters hooked up in parallel in order to get readings accurately. Okay, so here's a picture of a volt ohm meter. So we can switch these. You can switch them from volts to amps with the proper settings. You can find the resistance in a system. So these are all kind of built into one machine, and these are pretty nice. If you wanted to ever measure the voltage in your battery, maybe your car's not starting or something like that, it might be nice to have one of these. They're like 10 bucks, pretty cheap. And remember, measuring voltage, you could just put your test probes on 2 points in the circuit, so it'd just be positive and negative on the battery, and you can test the voltage going through the battery. Alright, so we're going to do a couple review problems before we wrap this up. So I want you to read through this and see if you can answer it before I go through the problem. You use an ammeter to read the current that's going through a resistor in a simple LED circuit. Your ammeter reads 0.01 amps going through the circuit, and you hold the connection for 10 seconds just to get a good reading. How many coulombs of charge pass through the circuit during your reading? So if you remembered, our equation is amps equals charge over time. And we have some values here. It's helpful to underline them so that way they kind of stand out, and it's also helpful to write them down. So time equals 10 seconds, and we're given an amperage, 0.01 amps. And we're trying to find the charge in the system. Okay, so let's plug them into our equation. 0.01 amps is equal to charge over time, which is 10 seconds. So again, multiply both sides by 10 to get that out of the bottom. Some algebra stuff here. So those are gone. 10 times 0.01, so it's pretty easy to do without a calculator. That's going to move my decimal place over 1. So the charge that I get is 0.1 coulomb. So an LED only moves 0.1 coulomb through the circuit, which is okay because LEDs do not use much charge at all to operate. Alright, so one more problem here. So we have a truck. The battery in the truck moves 720 coulombs of charge in 4 seconds. While starting an engine. What's the amperage generated by the battery? And this could be considered the cranking amps of the battery after we find it. So let's write what we have down. We don't know our amps. That's what we're looking for, cranking amps, right? We have our coulombs of charge, which is 720 coulombs, and we have our time, which is 4.00 seconds. So we're looking for those amps. Let's plug it into our equation. So amps equals 720 coulombs over 4.00 seconds. We're going to divide those out to get the amps that we're looking for, which is 180 amps. So we have 180 cranking amps to get that motor started. Okay, so this concludes our lesson here. So hopefully you understand how to calculate amps, charge, and time in a system, in an electrical system. So hopefully you know a little bit more about an electrical system after we're done talking about it. So thank you for watching.